Here we rederive the flow around the cylinder, but this time using complex potentials. And so what we want to find is the flow around a cylinder of radius A. And we will make it a little bit more complicated than last time. We'll assume that the flow at infinity is not in the x direction, but it makes an angle alpha with the horizontal direction. And we will assume that there is a circulation around the vortex, which we'll call gamma. In this case, we've discussed before, we can represent the flow with a uniform flow. The uniform flow for an incidence angle of alpha, or an angle of attack of alpha, is u exponential minus I alpha times z, plus a dipole. And here, because the dipole strength might be complex, I'm going to write it directly as a d exponential I delta, where d here is the modulus, so d is now real, exponential I delta, delta is the argument, minus I gamma divided by 2 pi log of z. This is here the complex potential associated with an irrotational vortex. So as discussed last Tuesday, we are not, now we have to derive, impose the right boundary condition, which is a no penetration boundary condition at the surface of the cylinder. But this time, instead of imposing it by saying that the velocity normal to the interface has to be equal to 0, which is the standard no penetration boundary condition here, we are going to use the complex potential and simply state that the surface of the cylinder, so this curve here, which has an equation r equals a, so r equals a and theta is free, we are going to say that this surface of a cylinder is a contour of the stream function. So another way of saying that is that psi, our stream function, on the surface of a cylinder, so for r equals a and theta, has to be equal to a constant. So from the complex potential, we know that the stream function is the imaginary part of the complex potential. So we just have to take here the imaginary part of our complex potential. So let me write our complex variable z in terms of modulus and argument. The modulus is going to be r and the argument is going to be theta. And so we have that our complex potential is equal to u exponential minus I alpha times r exponential I theta plus d exponential I delta divided by 2 pi r exponential I theta minus I gamma divided by 2 pi times log of r exponential I theta. And now we simply take the imaginary part of this complex potential. Now recall that we can write u exponential minus I alpha times r exponential I theta as u times r, exponential here I, if I put those two exponential together, theta minus alpha. Here, this is going to be d divided by 2 pi r, and we have exponential I delta here, minus theta here, and this, the log of r exponential theta is simply the log of r plus the log of exponential I theta, so plus I theta. So we have to look at the imaginary part of this complex potential here. The imaginary part of that is just ur times sine theta minus alpha, plus the imaginary part of this term here, and the imaginary part of this term is just d divided by 2 pi r times the imaginary part of that, which is sine of delta minus theta. And finally, the imaginary part of the complex potential associated with the irrotational vortex, which is just minus I gamma log of r divided by 2 pi. Okay, so this here is the stream function, and now we want to impose that condition here, that the stream function that the surface of the cylinder is a contour of my stream function, and therefore a streamline. So we look at psi at r equals a. So this is here the value of the function psi of our stream function along the surface of the cylinder, and we want to impose that this has to be equal to a constant. Right? But this is equal to here ua sine theta minus alpha plus d divided by 2 pi a times sine theta minus delta minus gamma divided by 2 pi log of a. So if this has to be a constant, note that this term is already a constant, and again that tells you that regardless of the circulation that you impose, the cylinder will be a contour, right, provided that these two terms cancel here. So for this to be equal to a constant, again that term is trivial because it's already a constant, so we have to make sure that these two terms, the sum of these two terms, is going to be equal to a constant. But here you have two sine functions with in principle two different phases. So you have one sine as a function of theta and another sine as a function of theta, and you know that there is no way that this is always going to be a constant regardless of theta unless it is precisely the same sine function, so unless alpha is equal to delta and the sum of those two terms is equal to 0. So for this to be equal to a constant, we need alpha to be equal to delta, such that this function of theta and this function of theta is the same. Otherwise, you will never be able to cancel those two terms for any given theta. And we need that ua plus d divided by 2 pi a be equal to 0. And so finally, this yields that alpha is equal to delta, and that d... Oops, sorry, I realized I made a little mistake here. Sorry, so here I wrote this too quickly. If you're taking the imaginary part of this, you have the sign not of theta minus delta, but you have the sign of delta minus theta. This is a delta minus theta here. Sorry, I wrote this not correctly here. And so if I write this in terms of theta minus delta, that's okay, but it's minus this, so I have a minus sign here. Otherwise, I don't get the same result as for the real potential. And so here, this is going to be a constant provided that this term cancels out that term, and therefore that ua minus d divided by 2 pi a is equal to 0, and that gives us a value for the dipolar strength of 2 pi a squared times u, which is precisely what we had before. So in terms of complex potentials, the complex potential for the flow around the cylinder is equal to the following. So this we already had, and here d is equal to 2 pi a squared u. So we'll have just an a squared times u left here, and this 2 pi disappears. Exponential I alpha minus I gamma divided by 2 pi log of z.